Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 10, Lesson 3 on horizontal shifting of functions. Now in the last lesson, we did vertical shifting of functions, which we achieved by simply adding or subtracting a positive constant from the overall function. Today we're going to be looking at horizontal shifting, which works a little bit differently than vertical shifting, but there are some similarities. So let's jump right in and see how this works. All right, horizontal shifting of functions. When we horizontally shift a function, we move it to the right or to the left by a certain amount. The pattern is similar to a vertical shift, but takes some getting used to. So let's kind of jump into it in exercise number 1. The graph of f of x equals the absolute value of x is shown below. The function g of x is defined by g of x equals f of x minus 4. Give a formula for g of x. All right, now this is a little bit weird. We haven't seen something exactly like this before, but keep in mind that f of x is defined as the absolute value of x. The better way you want to think about it is f of something is equal to the absolute value of something. So if g of x is equal to f of x minus 4, then g of x must be equal to the absolute value of x minus 4, right? Please note that that is very different than having the absolute value of x and then the minus 4 outside. If that was the case, the parentheses would be around the x and then the minus 4 would come outside. But if we've got something inside of these parentheses, then that should replace the x wherever it is. Now let's take a look at letter B. Using your calculator, produce a sketch of the graph of g of x on the same set of axes. Label it with its equation from A. Awesome. All right, so let's do this. Let's go into our graphing calculator. All right, I think I'm going to open up a new document here. Okay, and I'm going to add a graph, and the first thing I'm going to actually do is I'm going to put in an absolute value graph. Now that's actually a little bit difficult to find on this graphing calculator, but there's this button right here, it's right to the right of the 9 on the TI Inspire, that when I hit it, it's got all sorts of things. It's got square roots, it's got other types of roots, it's got things that I don't even know what they are. But way over here on the right, there's the absolute value symbol. So I'm gonna grab that, and I'm gonna actually put in the absolute value of x, just so that we have it there as our first function, right? So I want that thing sitting on my graph so that I can see it here. Now let's put in a second function. So I'm going to go into Menu, Graph Entry Edit, Enter. Now I've got this. So I'm going to go back into here. One of the great things is it's already on the absolute value symbol. And remember, I had the absolute value of x minus 4. And there it is. Let me just move that down a little bit, right? So I want to do a little sketch of this particular graph. Now, the most important thing to notice is it's exactly the same as the original absolute value graph. It's just been shifted to the right. How many units has it been shifted to the right? Well, we can tell that by looking very closely at the x-axis, and that's going to be hard for you to see. But that turning point is now at 4, 0 instead of at 0, 0. So literally, this thing has been shifted 4 units to the right. Okay, so it now looks like this. So I'm going to label that with g of x equals the absolute value of x minus 4. And again, real key that you've got that turning point there when x is equal to 4. All right, so simple enough. Now let me go back into my full screen, right? Important, letter C. Describe how the graph of f of x was shifted to produce the graph of g of x. Well, it's really cool, right? By subtracting 4 from the x before taking the absolute value, I have shifted the graph 4 units to the right. F of x was shifted or moved, however you want to put it, shifted 4 units to the right. Okay, and that is very important. F of x was shifted 4 units to the right. Okay, now let's just kind of put that to bed for a moment. Let's take a look at letter D. The function h of x is defined by h of x equals f of x plus 5. Give a formula for h of x and produce a sketch of it on the axes above. Label it with its equation. Okay, again, keep in mind, right, that f of x is equal to the absolute value of x. That's our original parent function. So h of x is going to be the absolute value of x plus 5, right? Again, whatever is in here replaces that because it's f of x plus 5. All right, so let's toss that into our calculator now. And first, let me just kind of, let me bring this thing back up. Exit out of here. I'm going to leave that other one on the graph. I'm going to put this thing in as my third one. All right, let me see. I want to again put in the absolute value. And now it's going to be x plus 5. And look at that. Now it's over here, right? Now I've taken that original graph and moved it to the left, okay? And specifically, if I look very closely, 1, 2, 3, 4, 5, right? This thing has now got a turning point over here at -5. So now this is h of x equals the absolute value of x plus 5. Okay. View, full screen. Now, we can see we've got exactly the same situation that we had before, letter E. How does the graph of h of x compare to the graph of f of x, right? Well, now f of x has been shifted 5 units to the left to produce h of x. All right. So let's take a look at letter F. Why are the two horizontal shifts we just observed somewhat counterintuitive? Now, before we get into that, remember with vertical shifting, if I added a positive number to the overall function, it shifted it up by that many units. And if I subtracted a positive number from the overall function, it shifted it down by that many units. And that makes all the sense in the world. On the other hand, right, when I did f of x minus 4, this moved right 4, and when I did f of x plus 5, this moved left 5. So that's a bit counterintuitive, right? Because we would almost have suspected that if we subtract 4 from the x, it would move to the left 4. And yet it didn't. It moved our entire function to the right 4. And when we added 5, you'd almost think that would move it to the right 5. And yet it actually shifted the function 5 units to the left. All right? And that's what we mean about counterintuitive. The vertical motion is intuitive. Add, you move up. Subtract, you move down. But with the horizontal movement, it almost works in the opposite of what you think. When you subtract directly from x, you move to the right, right? And when you add directly to the x, you move to the left, all right? And that is exceptionally strange, right? Horizontal shifting of functions. If k is a constant, then f of x plus k is a shift to the left by the absolute value of k, if k is positive, and f of x plus k is a shift to the right of f of x by absolute value of k units if k is negative. A lot of times, you just think about it as if I'm adding directly to x, then I shift to the left by that many units. And if I'm subtracting directly from x, I shift to the right by that many units. All right, that's assuming that we're adding and subtracting positive numbers, okay? So it's weird, because with vertical, add, you move up, subtract, you move down. On the other hand, with horizontal, subtract, and you move to the right, add, and you move to the left. And that is a bit weird, all right? So let's take a look at exercise number 2. A quadratic function f of x has a turning point at 5, 15. If the function g of x equals f of x plus 8, then at what coordinate point does g of x have a turning point? All right, so I don't know much about f of x, right? But what I do know about it is that it's got a turning point, let's say this is f of x. It's got a turning point at 5, 15, right? And then g of x comes along and is defined as f of x plus 8. So we're adding 8 directly to x, okay? Like we're adding 8 to x before anything else is done, all right? So what exactly happens? Well, g of x is f of x moved 8 units to the left, right? Because we're adding its 8 units to the left, right? Which means we'll get something like this. And where's my new turning point? Well, the y-coordinate's not going to change, but the x-coordinate is going to go from 5 down to -3, right? If I take that thing and I shift it 8 units to the left, suddenly my new turning point is going to be at -3, 15. And that's it, right? It's really that simple. But it is a little bit opposite of what you might expect. You might expect, if I've got f of x plus 8, I should just add 8 to the 5, and great, I have 13, 15. It doesn't work that way, all right? It's almost like this new function has an 8-unit head start on the old function because it gets to have 8 added to the x, and therefore it reaches its turning point 8 units sooner than the original one does, right? And that's kind of why it gets shifted to the left 8 units. Okay, let's keep playing around with this. Exercise number 3. Two quadratic functions are shown graphed below, f of x and g of x. The formula for f of x is f of x equals x squared minus 4. It is known that g of x equals f of x plus k. What is the value of k? Explain. All right, so what do you think? What is the value of k given that our original function f of x is this one, right? X squared minus 4, it's just our standard parent parabola that's been shifted down 4 units, right? And then I've got g of x, which is right here, right? And g of x equals f of x plus k. It's simply a horizontal shift. So what would the value of k be? Pause the video now and see how much you understand about horizontal shifts so far. All right, well, it's pretty simple. G of x is f of x that's been shifted by 1, 2, 3 units to the left. So g of x is f of x shifted 3 units left. So k is equal to 3, right? Because it's a leftward shift, we are going to add 3 units to make it shift to the left 3 units. Now, letter B, this is a bit more challenging. Find a formula for g of x in standard polynomial form. Show the manipulations that lead to your answers. Okay, this is really critical, right? Standard polynomial form. It's been a little while since we've talked about the standard form of a polynomial, but let's first get this thing down. We know that f of x is equal to x squared minus 4, and g of x is equal to f of x plus 3. Remember, we figured out the k was equal to positive 3. So if I want a formula for g of x, what I'm going to do is everywhere in this formula there's an x, I'm going to put an x plus 3. So g of x will be equal to x plus 3 quantity squared minus 4. All right, now that is a lovely formula for g of x. I love it so much, but it's not the standard polynomial form, right? For that, I've got to like square this x plus 3 out and then combine it with the minus 4. So let's do it, right? I need to do x plus 3 times x plus 3 minus 4, plus 3 minus 4. We can multiply these out however we want. I think I'll FOIL them out. So that's going to be first, outer, inner, last, and then I have to subtract off the 4. So that's going to be x squared plus 6x plus 5. Right? So there is my formula for g of x in standard polynomial form. Right? Standard polynomial form means that we've just got a term, another term, another term, another term, decreasing in powers by 1. X squared, x to the first, and then a constant. Okay. Finally, letter C, find the zeros of g of x by factoring. Circle them on the graph of g of x. Let me move this out of the way. All right, so I want to find the zeros of this particular function by factoring. So keep in mind, right, whenever I'm looking for the zeros of a function, what I'm doing is I'm solving the function set equal to 0. All right, well, I've asked you to do this by factoring. Why don't you pause the video now and go ahead and see what you get. All right, well, let's do it. I'm looking for two numbers whose product is positive 5 and whose sum is positive 6. Those numbers happen to be 1 and 5, right? So this factors as x plus 1 times x plus 5 equals 0. I can now take each one of these factors and set them equal to 0. And I'll get x equals negative 1. And I'll get x equals negative 5. And it says circle them on the graph. Here's that negative 1, and here's that negative 5. Right? The algebra supporting what we can see graphically. All right. Let's do one more problem with horizontal shifting. In our next lesson, we're going to combine both horizontal and vertical shifting, so we'll certainly get more use for this. But just as with vertical shifts, horizontal shifting of functions can also have practical applications. Let's take a look. Exercise number 4. A pump has a flow rate in gallons per hour given by the function f of t, which is graphed below, and where time is given in hours since midnight. Engineers want to shift the pump's operating hours by 2 hours later, but leave the pump rate pattern the same. They can do this by creating the function g of t equals f of t plus k. Letter A, produce a graph of g of t on the axes based on the shifting pattern by 2 hours forward. All right, that's simple, right? All I want to do is take this thing and move it 2 hours forward. So I simply take all my primary points, this one, and I'll move it 2 hours forward. This one, I'll move it 2 hours forward. This one, move it 2 hours forward. And this one, move it 2 hours forward. And this now must be my function g of t. All right, easy enough, right? I mean, if they say shift the graph 2 hours to the right, I should shift the graph 2 hours to the right. Now, letter B, what should be the value of k to produce g of t? Explain. All right, well, pause the video now and tell me what the value of k should be to produce this function g of t. Well, since we shifted to the right and we've phrased it as f of t plus k, k has to be negative, right? To move to the right, you need to either subtract a positive constant or add a negative constant. And again, the only reason I'm not saying that we should subtract here is because it's phrased as g of t equals f of t plus k. So k should be equal to negative 2 because it is a right shift by 2 hours. Or I could say by 2 units. Either way, right? Final piece. Oh, there's my nice graph, right? Letter C, what will be the pump rate at 9 a.m. in the morning if G of t is used? All right, well, this is simply reading off a graph. So see if you can figure out what the pump rate should be at 9 a.m. in the morning. All right, well, hours since midnight, 9 a.m. in the morning is going to be 6, 7, 8, 9. Here's 9 a.m. in the morning. So now I'm going to go up to my blue graph and go over, and watch out, right? This is in units of 2 gallons per hour on each tick mark. So that's going to be 18 gallons per hour. And that's it, right? Simple enough. All right, let's wrap this lesson up. Now, today we looked at horizontal shifting of functions, and it is definitely one of the more confusing topics in Algebra 1. When you add or subtract directly to the x variable before you do anything else in the function, it moves the original parent function either to the right or to the left in almost the opposite direction that you'd suspect. If you add a positive constant onto x, it shifts it to the left by that many units. If you subtract a positive constant from x, it shifts it to the right that many units. And again, that's very confusing. It literally works in the opposite way that the vertical shifting works. The vertical shifting, when we add, we move it up, and when we subtract, we move it down. In the horizontal, it kind of works the opposite way. We're going to, as I said, in the next lesson, combine both horizontal and vertical shifting together, because that can easily be done, and then we'll be able to make even more interesting and complex functions out of simpler parent functions. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.